This is the last lecture about pavement distress. We talked about mechanical distresses such as rutting, shoving, cracking, and we have covered also alligator cracks and log cracks and reflection cracks and all types of distresses. Then the concept of PCI, pavement condition index, was introduced and discussed as well. And as mentioned, there are two important distresses that are not covered by the PCI system. The first is roughness, and then through this concept of roughness, the IRI was introduced. And the last part of this pavement distress lecture deals with the skid resistance. Skid resistance, as not included in the PCI method, is extremely important for safety reasons. And here we'll just cover a very simple introduction to the skid resistance concept. Talk about the skid resistance. This is another distress that does not appear in the IRI, in the PCI method. So we have a wheel that is moving forward with a speed s, and it has a radius r, and there's it carries a vertical load F, Z. And so the wheel is moving forward and it has an angular velocity omega. So this is the situation. In the case of braking, the wheel is experiencing a force in this direction. And if we are thinking about the pavement only, then the pavement experiences the same Fz that the wheel exerts, but the force that the wheel was experiencing is now experienced by the pavement in the other direction. So this is a braking situation. Let's define the entities here. So S is the actual forward moving speed of the wheel. And then we have R is the wheel radius. And here I'm looking at a rigid wheel, so not including any radius changes because of compression of the tire or anything. Omega is the angular frequency of the wheel rotation. And we have Fz is the vertical force. On the wheel. And Fx is horizontal force due to friction. And we can think of mu as the ratio between Fx and Fz. Mu is basically what you call friction coefficient. Now let's define an entity called relative sliding. That's a G. G is defined as S minus R omega over S. I will renew the image here. So we have the wheel moving forward with actual speed S and rotating with angular frequency omega. What we have here is the forward movement minus the movement that is based on rotation. So S is actual speed, forward speed, and R times omega is a forward speed based on wheel rotation. So let's see. If, for example, we are traveling fast with our vehicle and then we hit the brakes and we lock the wheel. At that point, the rotation stops, omega is 0, but we still have the forward speed of the vehicle, at least initially. So in this case, the actual speed S minus 0 divided by the actual speed gives us a relative sliding of 1. So a relative sliding of 1, where G equals 1, represents the case of a lock wheel. This is the case where we skid with the locked wheel. If we think of another situation where the forward speed based on wheel rotation is the same as the actual speed we are driving at, then we have G equals 0 because S and R omega are identical. And then we can think of the other case where we are accelerating. And in the acceleration case, sometimes the wheel is rotating faster than the actual moving speed. And then G becomes negative because R times omega is faster than or larger than S. So whenever S is larger than R omega, we are in a braking situation. And whenever we have S smaller than R omega, then we are accelerating. And the chart that is shown also in the slide is G versus mu, where mu is the friction between the tire and the pavement surface. And based on testing, it has been observed that there is, of course, there is no sliding and there's no mu or any meaning from mu, because mu is defined as fx over fz, and fx is 0 here. But there has been tests to show this is G equal 1. This is where we have the locked wheel friction, that the friction coefficient is maximal at around 0.2. And then we are looking at the other case, the acceleration case. There is also some peak in the friction value, but then it can go all the way to almost 0. This is acceleration side, and this is the brake side. And what we have here is the friction at the locked wheel situation. And here we have the maximal friction, max, new max. And this is why many of the ABS systems are targeting a relative sliding of 0.2, because they are trying to maximize the friction. Up to now, skid resistance was dealt with in the case of dry conditions, but in reality, the problem is more severe and more relevant whenever there's water on the surface. So the problem with the water on the surface is that as the tire rolls forward, the water is expected to be pushed to the sides through these slits in the tire, and also utilizing the fact that the pavement surface is not perfectly smooth, but there is some texture. But there could be a certain speed beyond which the tire is moving so quickly forward that there's not enough time for the water to be displaced. And then the tire raises up because of a water pressure increase, and the contact is completely lost. This effect is called aquaplaning or hydroplaning, and it could occur at very high speeds. Of course, depending on the thickness of the water film on the surface and the dimensions of the tire. If there is some contamination in the water, for example, if the water is not clean but contains oils or dust, then the viscosity of the water itself is increased, and that means that the aquaplaning speed is reduced. This makes the problem more severe. Of course, if there are contaminants like dust or particles that clog the pavement texture, then the texture itself becomes a bit more smooth, and the ability of water to escape below a rotating tire is further diminished. When looking at the effects of texture, texture has at a very small scale, a micro scale, has an effect of breaking the thin fluid surface and allowing the water to flow. So it's not just the mesotexture or macro texture that helps with skid resistance, it's also the macro texture. Overall, the problem of skid resistance is relevant under winter conditions, wet conditions, or icy conditions, and therefore most of the devices that are utilized for measuring skid resistance in pavements apply some controlled thickness of water film before performing the test. So the tests are usually done over dry pavements that are wetted specifically for the evaluation of the skid resistance. The level of skid resistance usually deteriorates over the years, starting from some slight increase when the pavement is newly paved, and then decreasing continuously along the life of the pavement due to breakage of the texture and polishing of the aggregates.